In our previous step, we have already formed the nodal diagram just by looking at this mechanical rotational system over there, and I have already given you how to construct this nodal diagram over there. Now the next step is quite naturally the simpler one. If you do apply the D'Alembert principle on each and every node of our considered point, we are having our differential equation just by applying our D'Alembert principle for our mechanical rotational system. So let us just go for that one. If you do apply the D'Alembert principle on our node 1, we have got what is the D'Alembert principle? The summation of our applied torque plus our resistive torque, the summation of these two opposing torque value will be 0. Okay. So if you do apply the D'Alembert principle on our node 1, we have got the applied torque minus our resistive torque. So what are the resistive elements that has been considered at our node 1? The resistive elements are J1 d2 theta 1 t divided by our dt2 for this one minus our k1 theta 1 t minus of theta 2 t minus of theta 2 t, that will be equal to 0. Now if you do transfer the elements of the resistive elements of our J1 and K1 to the another side of our expression, the final form will be this one. So let us just go for that final form. The final form will be the applied torque, which is equal to our J1 d2 theta 1 t divided by our dt2 plus K1 theta 1 t minus of theta 2 t. So this will be our first equation. Okay. Now if you just do the same procedure just by applying the D'Alembert principle on our next node, which is our node 2, what will be the equation? The equation will be this one, which is minus J2 d2 theta 2 t divided by dt2 for this one minus K2 theta 2 t minus of theta 3 t for this one minus K1 theta 2 t minus of our theta 1 t, that will be equal to 0. Now if you do take the common of this all this minus and do transfer to the another side of our expression, this minus will become our plus. So ultimately the equation will be this will be plus, this will be plus, this will be plus, and this is our second mechanical equation if you do apply the D'Alembert principle on our node 2. Similarly, if you just go for that same procedure just by applying the D'Alembert principle on our node 3, we are having the equation as this one. So let us just write down the equation, which is J3 d2 theta 3t divided by our dt2 for this one minus b3 d dt of our theta 3 for this one, and let us just go for that common part for k2 and k3. So first I am just going to take the k2, so minus k2, this one will be theta 3 minus of theta 2t minus k3, this one will be our theta 3 minus of theta 4t, that will be equal to 0. Now if you just go for the same procedure, if you just do take the common of minus for both all these expressions over here and do transfer to the another side of our expression, the expression will be ultimately look like this one. So this is our, so all the minus will become our plus 1. So this is our third mechanical equation over here. And for the last part, if you just go for that same procedure just by applying the D'Alembert principle on a node 4, what will be the equation? The equation will be this one. The equation is minus J4 d2 theta 40 divided by our dt2 for this one minus b4 d dt of our theta 40 for this one, and let us just go for that common part, the k3. So for that k3 we are having minus k3. This one will be our theta 43 minus of theta 33. Theta 43 minus of theta 33, that will be equal to 0. So this will be our fourth mechanical equation. Now once again, if you do like to transfer the minus, or if you do take the common of or minus for all these expressions for our J4, B4 and K3, and do transfer to the another side of our expression, which is quite naturally the 0. So this minus will become plus. So these are our four different equations just by applying the D'Alembert principle over here. I am just going to repeat this portion once again because this portion is very, very important. First, we have formed the nodal diagram from this conventional mechanical rotational system over there, and after that the diagram is look like this one. Now the next step is quite simple. If you do apply the D'Alembert principle on our each and individual node, we are having these four distinct or four different equations over here. And how do I get to that consideration? We are just having, or we are applying the D'Alembert principle over here. So what is the D'Alembert principle? The D'Alembert principle will be quite naturally the applied torque plus our resistive torque, the summation of these two separate torque or two opposing torque, the applied torque plus our resistive torque, the summation of these two torque element will be 0. So how do you apply that consideration? If you do apply the D'Alembert principle on our node 1, we are having this equation. So quite naturally the applied torque minus our J1 d2 theta 1t divided by dt2 minus of as the in between our k1, as the k1 is present in between our theta 1t and theta 2t, because of that one the resultant angular displacement will be our theta 1t minus of theta 2t, as the k1 is being present in between our theta 1t and theta 2t over here. And why do I consider that theta 1t is greater for this consideration? Because we are applying the D'Alembert principle at our node 1. Because of that, we are taking that the theta 1t will be greater in this case or in this consideration. So for that one, we are having this equation, just applied torque plus these are resistive torque, and we do know that the resistive torque is always opposing our applied torque over here. Because of that consideration, we are having all those torque values as our negative sign value over there. So applied torque minus our resistive torque plus our resistive torque, that will be equal to 0. So we are having this first equation over here, and after rearranging that one, we are having the equation 1. Similarly, if you do apply the D'Alembert principle on our node 2, here the applied torque is none. You can see that there is no applied torque that is being present at our node 2 over here. So all those torque elements are having the negative value over here, and because of that the 2 is connected with our J2, and this is our point minus J2 d2 theta 2t divided by d2 dt2, and as we are taking theta 2t as our reference factor over here, so the resultant element or resultant angular displacement for our k2 and k1 will be look like this one. So for this case the theta 2t will be greater as we are applying the D'Alembert principle at our node 2. Because of that consideration, the k2 is been present in between our theta 2t and theta 3 over here, and quite naturally the resultant angular displacement factor will be our theta 2t minus of theta 3, and for our k1 the resultant angular displacement will be the same one, which is in between our theta 2t and in between our theta 2t and theta 1t. Because of that consideration, we are having theta 2t minus of theta 1t, and we are just taking the common of all this minus factor over there and do transfer to the another side of our equation. After that, we are having our equation 2. Similarly, for that next part, we are having our equation 3 over here just by applying the D'Alembert principle on our 3 over here. And for that case, we can see that with our theta 3, the J3 and B3 has been connected over here. So I have included the J3 expression, the B3 expression over here, and quite naturally the K2 and K3 are connected in between our node 2 and 3 and in between our 3 and 4 over here. And in between this resultant angular displacement case, the theta 3 will be greater. Why? Because we are applying the D'Alembert principle at our node 3. Because of that consideration, the resultant angular displacement for our K2 and K3 will be theta 3 minus of theta 2 and this one is our theta 3 minus of theta 4 3. So we are forming that equation, and if you do take the common of minus for all this expression and do transfer to the another side of our equation, we are having this equation 3. So for that last consideration, or for the last case, we are having this equation 4 over here. And how do I get to that point, or how do I get that equation? Just by applying the same procedure over here, which is just by applying the D'Alembert principle on our node 4. So J4, B4 are connected over here, and the K3 is present in between our 4 and 3 over here, and the resultant angular displacement factor for that case will be our theta 4 3 minus of theta 3 over here, which is equal to 0. And once again, if you do take the common of minus for all this expression and do transfer to the another side of our expression, we are having our equation 4. So this is the exact way on how to form the D'Alembert principle, or how to apply the D'Alembert principle on our each and individual nodes over here. So this is our next step, and just wait for my next part.
If you like my video, so what are you waiting for? Please do subscribe my channel, hit the bell icon for more updates, and stay tuned to the channel. Thank you and goodbye.